Here we have the graph of sine theta. Notice its shape. It has a period of 2 pi. That is, it repeats every 2 pi. And actually the graph continues forever. So its domain is from negative infinity to infinity. It can accept any value. Its range, though, is restricted. The only outputs you get from sine theta are between and including -1 with the minimum value and +1 as the maximum value. And what we have here is a many to one function. That is, if we just look at this section of the graph of sine theta, we've got 1, 2, 3, 4, 5 possible inputs that are different but give the same output of 0. We can also look at these values here. The output here is -1 when the input is minus pi by 2, and the output here is -1 when the input is 3 pi by 2. So we've got a many to one relationship for this function. That's going to be important later on. Now we're going to look at the graph of cosec theta. Just placing a piece of tracing paper on top because it's useful to have the graph of sine theta drawn to help us work out what cosec theta looks like. Cosec theta is the reciprocal of sine theta. That is, cosec theta is 1 over sine theta. Now looking at sine theta, it does have an output of 0 at times, and we can't divide by 0 because it's undefined. So what we're going to get straight away are asymptotes at the values when sine theta equals 0. Let's draw those on now. So each of these dashed lines represent asymptotes where our value of cosec theta becomes undefined because we cannot divide by 0. Let's look at what happens to the graph of 1 over sine theta between 0 and pi. Well, really small values, really small positive values that are close to 0 are going to give us a large output. So when we do 1 divided by a really small number, we get a large output. So actually, from the left, it's approaching infinity is the output. So I'm going to get this shape, and similarly, it's going to happen here as well. Because as it approaches pi, and remember, pi itself gives us an output of 0. Sine of pi is 0. So if we get a number that approaches pi, just slightly less, then we're dividing by a small number, a number really close to 0, but positive, and it's going to give us a really large output. So for this section of the graph, we get this shape. With this bit here, pi by 2 has an output of 1. Now this graph never touches the asymptote at this value. Similarly, we're going to get the same shape here, only upside down. And again here. And again here. So this green is the line y equals cosec theta. In an exam, it can be helpful to sketch a graph of sine theta first, and then draw your graph of cosec theta afterwards. But make sure you clearly label which graph is which. Here we have the graph of y equals cos theta. It's the same shape as sine theta, but it's a translation of that graph. It has a maximum point at 1 and a minimum point at -1. So just like the sine graph, it can accept any value in its domain. So it has a domain from -infinity to infinity, but its range is restricted. It has outputs from -1 to 1 inclusive. Just like sine, this graph also has a period of 2 pi that it repeats every 2 pi. This time we're going to look at the graph of sec theta. And sec theta is the reciprocal of cos theta, that is 1 over cos theta. So similarly to the last example, we're going to look for where cos theta equals 0, which means that our graph sec theta is undefined. So once again, we're going to get asymptotes at these values. That is the values of cos pi by 2 here will give us an output of 0, and we can't divide by 0 because it's undefined. Let's draw those asymptotes on now. Now we've got our asymptotes, we can draw the rest of the graph within these boundaries, and it looks very similar to the graph of cosec theta. So here we have the graph of y equals sec theta. And in an exam, it can be helpful to draw the graph of cos theta first, making sure you mark on the values of 1 and -1, and then on the x-axis, or where we've got theta, pi, 0, let's put that there as well, 2 pi, minus pi, 2 pi, or whatever values you've been asked to draw the graph for. Remember, the graph doesn't touch these asymptotes, but there are points where the graph of cos theta takes the same value as the graph of sec theta, and that's here, -1, or here, +1. Here we have the graph of y equals tan theta. Notice it already has asymptotes drawn on it. That's because tan theta is the same as sine theta over cos theta. So where cos theta equals 0, we get these asymptotes for the same reason as before. You can't divide by 0, it's undefined. So tan doesn't have a domain from -infinity to infinity because there are certain values that it cannot take. For example, pi by 2 or 90 degrees. But the range of tan goes from -infinity to infinity. Tan has a period of 1 pi or 180 degrees. That is, it repeats itself every 180 degrees or pi. Now the reciprocal of tan theta is cot theta. Now let's look at our graph again and look at where the values of tan theta equals 0. And that's where our asymptotes for cot theta will be. So we're looking at -2 pi, minus pi, 0, pi, and 2 pi. Let's draw the asymptotes there. Now we've got our asymptotes in position, we can draw the rest of the graph. Unlike the other graphs, it's not always that useful to draw the tan graph first. Certainly not to draw in all the asymptotes as well. So it's a good one to learn off by heart. Let's look at what the graph looks like without tan. So here we have the graph of y equals cot theta. Back to the sine graph, we already mentioned that it's a many-to-one function. So if we were to do the inverse of sine, it would become a one-to-many function, which is not allowed because a function has to be many-to-one or one-to-one. So what we have to do is restrict the domain of sine theta so that we get a one-to-one function in the inverse, and therefore it can exist. So I'm going to restrict the domain from pi by 2 as the maximum and minus pi by 2 as the minimum. So if I restrict the values of theta from negative pi by 2 to pi by 2 inclusive, then I only get a one-to-one function. Therefore its inverse will also be 1-to-1. Let's zoom in on this section of the sine graph. Here I have a zoomed in section of the graph for sine theta, and I've also drawn in the line y equals theta to show the reflection a bit easier. So it's got the domain from minus pi by 2 to pi by 2, and it's got a range from -1 to 1. A great way to do this is to use some tracing paper. So I'm going to trace my graph and the axes. Now that I've traced the graph and the axes, I can flip the tracing paper to realign the axis for theta where the axis for y is, and therefore the axis for y where the axis of theta is. And that reflects the graph in the line y equals theta. If I carefully line it up with the origin, you can see what the graph of the inverse function, that's the graph of the inverse of sine, looks like. This is a great tip when drawing a graph in the exam. Don't forget to label it. And remember, the domain of the inverse is the range of the function, and the range of the inverse is the domain of the function. It's also good practice to label these points on the diagram. So here, this orange line represents the graph of the inverse of sine theta. Here again, we have the graph of y equals cos theta, which is a many-to-one function. So to get the inverse of this graph, that is the inverse of cos theta, we need to restrict the domain so that we have a 1-to-1 function. So if I restrict the domain from 0 to pi, then all the inputs in that interval will give me one unique output. So if the function is 1-to-1, then the inverse will also be 1-to-1. So I'm just going to zoom in on this section of the graph here. Here we have the graph of y equals cos theta for the interval 0 to pi. So it's just that section of the graph. I've also drawn on the line y equals theta. So this graph will be reflected in that line to give us the inverse of cos theta. Let's get the tracing paper and work out what it looks like. Once I've traced the axes and my graph, I can then flip the tracing paper to align the axis for theta for y and the y-axis for theta. Notice I've also marked on this point here as a point of reference. If I line this up, if I line up the origin, we can see what this graph looks like. So this graph here, the orange line, is the graph of the inverse of cos. Let's just bring that down a bit so you can see it a bit better. Then we're going to mark on these key points here. So this point here is the value of 1, and this point here is the value of pi by 2, which makes this point here, the top of the graph, pi. And this orange line is the graph of y equals the inverse of cos theta. The domain of the inverse is the range of the function. Remember, the range of the original function was -1-to-1. So the domain of the inverse is -1-to-1. And the range of the inverse is equal to the domain of the original function. So the range here is 0 to pi. Back to the tan graph, and we can see that tan again is a many-to-one function. So if we want to draw a graph of the inverse of tan, we must first restrict the domain of this function tan. So I'm going to restrict it from -pi by 2 to pi by 2. So just looking at this interval here from -pi by 2 to pi by 2, we can now work out the inverse of tan. When it comes to the domain and range of tan theta, the domain, it cannot equal minus pi by 2, and it cannot equal pi by 2. So we've got curved brackets on the domain, and then the range is from negative infinity to infinity. Let's trace this shape. Now that I've traced the axes, the shape of the graph, and the asymptotes, I can flip the paper to look at what the inverse of tan looks like. Realigning the axes, I can see the shape of the graph. Let's remove the tan graph. There we go. And if we've marked on theta and y there, we can see that the domain of the inverse of tan, let's write down that graph first. This is the graph of y equals the inverse of tan theta. We can see that the domain takes any value from minus infinity to infinity, but its range only goes from minus pi by 2, curved bracket, to pi by 2, curved bracket. Let's check that against the tan. So tan, the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. To finish up, I'm just going to mark on these points here. So we've got here, we had pi by 2. Down here is minus pi by 2. So this is the graph of y equals the inverse tan of theta.